just want to say how very pleased I am to get to be part of this department and part of this event. So welcome to all of you. I want to talk just kind of generally in an overview and heuristic way about the goals of the research that I've been carrying out for the last several years. I am trying to make computation for certain kinds of models. I'm a Bayesian environmental statistician, so spatial and environmental models, possible for anybody to run. And when I'm thinking about anybody, I mean the high school kid with a netbook or a gaming machine, or the person in a desert with solar power to drive a computing machine. So I changed the title on Dale a little bit and made it affordable and portable. Let's see. Control L, thank you. And then what do I want to do to change the next slide? That. We're in here. All right. So what do we need as characteristics of software and hardware? Well, the software has to be free and open source. It has to run on hardware that's both inexpensive to purchase and requires low power to run. The software must run on a wide variety of platforms. We don't know who our target audience are. Do they have desktops, laptops, tablets, gaming machines, phones, or something else that hasn't been invented? So one way of making computation fast and feasible on low-cost hardware is parallelization. It's been learned years ago that it's more efficient to distribute computation over multiple low-power cores than to try to increase computational speed and power of individual computing cores. So there have been a lot of different parallelization strategies in hardware. Clusters of multiple computers. That's not going to meet my aim of available. Multi-core CPUs, maybe, but they tend to be expensive and high power. How about many-core accelerators, such as graphical processing units? Well, that's the direction that I chose to go. And I'm going to show you some baby steps in the final direction. I'm not there yet, I'm getting close. So, graphical processing units, or GPUs, as you know, are just the familiar graphics cards that control the displays on our computers, such as that one. They have many cores, tens, hundreds, in the most modern ones, even thousands of cores, designed essentially for the simple arithmetic operations that are needed to put pixels on a screen. In particular, they're optimized for all cores to form exactly the same instructions, but on different data. And all cores can execute simultaneously. So those last two characteristics kind of determine the kinds of computing problems that are going to be feasible to be parallelized this way. The first language that has come into extensive use for scientific computing on GPUs is NVIDIA's CUDA, or Compute Unified Device Architecture. It's proprietary to NVIDIA Corporation, runs only on their GPU. So it's a wonderful tool, but some steps back from where I'm trying to go with this generalizable program. What CUDA does is it extends C programming language with commands that enable us to split computational work between the CPU and the GPU. The CPU as a host coordinates the overall execution. Now here are some more critical points. CUDA lets us transfer data from the main memory that the CPU can talk to the GPU's memory. They're separate. And so there's a lot of communication involved in sending data from the main memory to the GPU. And the GPU does its very fast computation, but then it has to send the results back. So it's that communication that becomes the bottleneck. All right. Now, let's think about adapting Bayesian computing to GPU parallelization. Obviously, the stalwart of Bayesian computation, Markov chain Monte Carlo, isn't a promising computational candidate because of its inherently serial nature. We need the results of iteration 1 before we can do iteration 2. We can't throw everything out to 1,000 GPU cores and tell them to go at it. So my alternative idea, which is certainly not unique to me, but happens to work very nicely in the class of hierarchical spatial models is let's marginalize our posterior density. So we bring it down from a high dimensional domain to a very low dimensional. Then let's reparameterize that low dimensional marginal distribution so we can put it on a nice, simple domain, such as a simplex. And then we're all set to implement rejection sampling by having the GPU evaluate the marginalized posterior density on candidate values. We're asking the GPU to perform exactly the same computation on different input data, namely the candidate values of rejection sampling. And once we have samples from the marginalized posterior, we can always transform back to the regular marginal posterior and generate the rest of our parameters conditional on those samples. So proof of concept was the R package CARRERS, which with the help of two then undergraduate students, Stephen Monet and Michael Seedorf, I put on Cran in 2012. It does reparameterize and marginalize posterior sampling. The RAMS part is that last, for conditional autoregressive models. That's where the CAR part of the name comes from. It draws independent samples from the posterior distribution of these Bayesian conditional autoregressive models. So that's another nice advantage too. You don't have to deal with Monte Carlo convergence assessment. You don't have to adjust the variances of posterior means and so forth for autocorrelation. For example, because there isn't any. Let me just give you a quick example to show what kinds of models this package can handle. So this is data that originated from satellite images, but it's been processed into what's called NDVI, Normalized Distance Vegetation Index, that gives us a sense of the intensity of vegetation that we're looking at. And I see just how washed out this looks to you. Yeah. Okay, well, we'll do the best we can here. I used color schemes that make what's supposed to be, on my screen, this looks like a really vivid green, to show the most intense vegetation. And as we go through yellows and pinks and whites, it's showing less and less intense vegetation. So this is actually southwest Iowa and eastern Nebraska. The cities show up as the least vegetation intensity. So this would be Lincoln, Omaha, Des Moines, and that little pink thing up there, yeah, that's it. Now, just to show what the package can do, that's the actual image. And I threw some random noise into it, and then fed this data into the CAR-RAMS package. It can estimate the strength of association in the east-west direction, independently the strength of association in the northwest direction, and measurement error, overall mean, regression coefficients for linear trends in the east-west, north-south direction. And then given all those things, it can estimate the underlying posterior means of the true values. So this is what it got back out in an attempt to recreate the true image. It didn't do a perfect job, it didn't do a bad job. Okay, so that's out there. So we've got something that parallelizes this Bayesian computing, but it certainly isn't on inexpensive, accessible hardware. The next step was let's find something other than CUDA to do the GPU parallelization. So that led me to OpenSea. It was devised by the Kronos Foundation, which is a nonprofit consortium of various vendors and academics and so on. And they have written this standard, well, let me use their words, this came from the Kronos Foundation's website. OpenSea is the first open, royalty-free standard for cross-platform parallel programming of modern processors found in personal computer servers and handheld embedded devices. Open source, royalty-free, runs on all kinds of different hardware. We are getting more. So vendors, hardware vendors, implement the OpenSea standard by providing shared libraries to which programmers can link programs. So it's somewhat more cumbersome for the programmer to code in OpenSea than in CUDA, just because of this generalizability. It can run on so many different kinds of hardware. I think that's probably why OpenSea has not become popular. On the other hand, there are a lot of hardware vendors that implement OpenSea. So OpenSea code can run can be portable across AMD, ARM. Oh, look, Apple's in there. They actually are the ones who started OpenSea and asked the Kronos Foundation to develop it. IBM, NVIDIA, so there are many, many platforms in which this can run. So in 2013, with help from two then master's students, Juan Cervantes and Alex Sawyer, I developed the car ramps OCL package. It's basically car ramps, but with CUDA calls rather than, with OpenCL calls rather than CUDA. And I've tested it on a variety of hardware, and it certainly would run on many other ones. Anything that ARC would run on that had an OpenCL implementation for it. I want to show you the contrast between running car ramps OCL on two different machines. This one is a lab machine. Many of you know and love LDAT LNX 214. So it's a mid-range computer. It has an Intel Core i7, so nice GPU, and a business class decent GPU. The other piece of hardware is my network. Unlike the lab machine, whose processor draws 150 some watts, whose GPU draws an additional 62 watts, my network has a fusion processor, GPU and CPU together, which draw a whopping 4.5 watts. I paid $220 for the entire thing. Much slower cores, much slower and smaller GPU. But let's look at some results here. These are for a data set these are for data sets, I should say, that are three-dimensional. So let me go back for 1 second too. I get it, okay. Right little job in there when my slide was too big. So the data sets are of size 10 by 10 by 10, or 15 by 15 by 15, or 20 by 20 by 20. And I'm showing you times to obtain 200 independent samples. The panel over here is on the lab machine. The panel over there is my little computer. We see exactly what we would expect in the sense of this is with CPU only, takes more seconds than when it's accelerated with OpenCL. As we go to bigger and bigger data sets, the advantage becomes bigger and bigger. We see the same kind of pattern over here for the little guy. Obviously, more seconds, taller bars are bad, so it's slower than the lab machine, than what we would expect. But we see that the CPU is much slower here than the GPU. I want to go to a slide that makes a slightly different comparison, which is this one. Intel's logo is in blue, AMD's is in black, so I use those colors to code the bars. What I'm contrasting here is the Core i7 alone, without GPU acceleration, compared with the little joint processor in my machine. And you can see that this little fusion processor wins the game when we use its GPU acceleration. Now, we're still not all the way there. We're still dealing with that bottleneck of transferring data back and forth from the CPU component of this fusion processor to the GPU component. Typically in these system on a chip, we still have separate memories for the CPU and the GPU. So in my OpenCL code, I'm still doing all this transferring. And that accounts for some of the tall heights of these bars. But what exciting new developments are on the hardware and software? Interestingly enough, AMD is actually starting to make fusion chips where there's a shared memory between the CPU and the GPU. And I actually chose my little network because it actually has one of those early models. I'm not exploiting that capability yet. I'm just using regular OpenCL. But there is a new foundation called the HSA Foundation for Heterogeneous System Architecture. And they're creating a specification for hardware that has this kind of intercommunication, shared memory, and also other advantages in how the CPU and GPU components or other devices for acceleration besides GPUs can talk to each other. And they've developed a language that is sort of like the grand OpenCL for these new devices. And Now, even if there's a new language, are programmers going to run to adopt it? No, not if it's not easy, and not if there aren't compilers. Well, look at this little fly-by-night organization here, Microsoft, who has developed a compiler, which runs on both Windows and Linux, which is specifically for code for these machines with shared memory. So it's, say here, it supports the sharing of physical memory between heterogeneous devices, meaning you said you wanted to use that shell.